So this is another example of some integration techniques. In this case, we're going to be dealing with partial fractions. So we have integral of x squared plus 5 over x cubed minus x squared plus x plus 3. So just looking at that, you sure as heck don't want to try to do any kind of u substitution. Splitting that apart is not going to help you in any way, shape, or form. So we're going to see if we can decompose this into some couple of different fractions and go from there. Alright, so first of all, we got to be able to factor the bottom. So let's just consider x cubed minus x squared plus x plus 3. Now that's not one that we can factor right off the top of our head, so there's several different reasons why I'm doing this example. So first of all, if we can't just look at it and see how we could factor it, then we got to use some synthetic division. So we got to check the factors of 3. So positive 1, negative 1, positive 3, negative 3. Now I'm going to go ahead and skip to one that works, so I know that negative 1 works, so I'm going to put negative 1 in the box. And we have 1, negative 1, 1, and 3 doing our synthetic division. So I bring down the 1. Negative 1 times 1 gives me negative 1. That gives me negative 2. Negative 1 times negative 2 gives me positive 2. 1 plus 2 gives me 3. And negative 1 times 3 gives me negative 3, and so I get 0 like I want. So, since I've checked since I checked negative 1, my factor that I'm checking is x plus 1, if I could speak. So, I can rewrite this as the integral of x squared plus 5 over, and what I have is x plus 1 times, and then I have x squared minus 2x plus 3. Now, x squared minus 2x plus 3 is not something that we can factor by looking at it with rational coefficients. We'll probably have some irrational stuff in there, so we're going to leave it like that for the sake of what we're going to do with partial fractions. Alright, so using my partial fractions, what I now know is that I can write, using my definition of partial fractions, I can write x squared plus 5 over x plus 1 times x squared minus 2x plus 3. By definition of partial fractions, I can write that as some a over x plus 1, that's one of my factors, plus, and since that's a polynomial that has a power of 2, x squared minus 2x plus 3, then that means my numerator could possibly be linear. So it could possibly be either linear, bx plus c over x squared minus 2x plus 3, or it may just be a constant. It may just end up being a constant c, and we'll see just a minute it does end up just being a constant. But you don't know, so you got to check it and see. Alright, so doing our partial fractions trick, if we now multiply this entire expression through by my common denominator, so my common denominator being the denominator, so I'm just going to put LCM here, I don't want to write that all out, just save myself some time, then what it boils down to that I get to is I get that x squared plus 5 has got to be equal to a times x squared minus 2x plus 3 plus, and then x plus 1 times bx plus c. That's what my partial fractions tells me. Alright, so now, no way around this. You're going to have to multiply all this stuff out. So I know that x squared plus 5 is going to be equal to, this is not a short process by any means. So this is going to be ax squared, excuse me, minus 2a times x plus 3a. And if we multiply these two binomials together, we get bx squared plus cx plus bx plus c. Alright, so now, if we rearrange and group some stuff together, I know that x squared plus 5 has got to be equal to, I can take my x squareds, my ax squared and my bx squared, put those together, and so that says that a plus b times x squared. Put all my x's together, so if I put all my x's together, negative 2ax, cx, and bx, put all those together, then that's plus, and I have negative 2a plus b plus c times x plus, and then I have 3a plus c. Just grouping all my like things together, which is one technique that you have for partial fractions. Alright, so that tells me that a plus b has got to be equal to 1 because on the left-hand side the coefficient in front of x squared is 1. I have no x, so that tells me that negative 2a plus b plus c has got to be equal to 0. And I know that 3a plus c has got to be equal to 5. Alright, now, how you proceed from here is your choice. You can take any one of those that you have and start rearranging some stuff. But I'm going to do this. I'm going to say that b is 1 minus a. And down here, I know that c is 5 minus 3a. So I can use both of those in my middle equation. So that gives me that negative 2a plus b, which is 1 minus a, plus c, which is 5 minus 3a. All that's got to be equal to 0. Just use my first and third equation to rewrite my middle equation in terms of one variable. Alright, so I have a negative 2a, negative 3a, negative 2a, negative 1a is negative 3a. Negative 3 or more gives me a negative 6a. So negative 6a plus 6 is equal to 0. And that tells you that a is equal to 1. Doesn't take you long to get to that. So that tells you that a is 1, which tells you over here that if a is 1, then 1 minus 1 gives you that b is 0. And if a is 1 over here, that gives you c is 5 minus 3, which is going to be 2. So I now have my values for a, b, and c, respectively. So, back up in my original problem. I can rewrite x squared plus 5 over how I factor my denominator of x plus 1 times x squared minus 2x plus 3. I can rewrite that as follows. So I can read my integral. Alright, so the integral of x squared plus 5 over x plus 1 times x squared minus 2x plus 3. I can rewrite that into these two pieces. The integral of a was 1, so this is 1 over x plus 1 plus, and b was 2, so this is 2 over x squared minus 2x plus 3, all that dx. It's a lot of work, but that will get you to what you need to do this with integration by using partial fractions. Alright, so now I'm going to give myself some room. The first piece, no problem. Integral of 1 over x plus 1, that's the natural log of the absolute value of x plus 1. No problem with that piece. Plus, the second piece I still got to do some work on. This is 2 over, and something that looks like this just screams to you to rewrite it with completing the square. So this is going to be x squared minus 2x. Half of negative 2 is negative 1. Square that, you get 1. So plus 1, turn around, minus 1, and then plus 3. Add and subtract 1 in there. Dx. So this is the natural log of the absolute value of x plus 1 plus, and this is the integral of 2 over, and that becomes x minus 1 squared plus 2. And that fits the form that we have for arctangent. This is this is a u squared plus an a squared, or a squared plus u squared, either way you want to look at it. So that fits exactly like I want. So my u is x minus 1, which tells me that du is dx, so I'm good with that. I don't have to do any kind of substitution there because du is dx. And that tells me a squared is 2, so that tells me that a is the square root of 2. Alright, so we're home free now. So this is the natural log of the absolute value of x plus 1 plus 2 times, got the 2 in the numerator, and then 1 over the square root of 2 times the arctangent of x minus 1 over the square root of 2. So the arctangent of u over a. And then we can rewrite this just a little bit nicer. This is the natural log of the absolute value of x plus 1 plus 2 over the square root of 2 we can simplify as just the square root of 2. So this is the square root of 2 times the arctangent of x minus 1 over the square root of 2. And since this is an indefinite integral, we'll put the plus c on the end there to get the integral there. Again, the reason why you have to use partial fractions is because when you take derivatives, you end up combining stuff into one single denominator. So trying to undo that whole process with integration leaves you having to decompose that to get back to something that you can integrate. And again, that was just a matter of us doing the partial fractions. And there's a couple different techniques you can use. I wanted to illustrate that just to remind you about synthetic division, because that's not something people remember about all the time. And then also to make sure you remember that since this trinomial over here has a power of 2 in it, that numerator, you have to at least consider the fact that that numerator could be linear, so you have to use a bx plus c in there whenever you set up your partial fractions. And again, in this case our b ended up being 0, but that's not always the case, so you have to make sure you account for that when you set up your partial fractions. Okay, so again, just one example to hopefully help you with some different things with partial fractions. There's many different kinds of examples I can do, but I try to pick that one just to illustrate a few of the concepts to you, and hopefully that will help you.